In this video series on the energy efficiency of heat pumps, today we're going to talk about a rather special seasonal indicator, the SPR, which is intended for air-to-water and water-to-water chillers, but specifically for so-called process chillers used in industry. We'll see that their operation is a bit different from the ones we discussed earlier, like the SER and those that worked with SER and SCOP, since some of those referred to comfort applications, but not to the specific operation of process chillers. We already saw in the first video the concept of EER and COP, that snapshot in time. Later, we looked at the concept of seasonal COP, which would be like a video, the average EER and COP over the whole year. In this case, we're going to look at process chillers, and then we'll discuss the ETAs, the seasonal efficiencies. As we've mentioned so far, these concepts refer to final energy, whereas ETA refers to primary energy. It's a concept that we'll see ultimately shows that heat pumps truly have a very strong renewable character. My name is Jose Arboleda. I am the Training and Regulatory Manager at KEYTER. All right, as always, the first thing we need to do is take a chiller, in this case, an air-to-water unit. And when we look at the data sheet, we find this SEPR both at 7 and at -8. And what does that mean? Well, if we go to note 6, thank you, we see that the CPR is the seasonal energy performance factor for high temperature. Now let's see what it means for high temperature. It's the S12, and they're calculated according to 14.825. Also, in addition to 14.825, which is used to calculate the SEER, the SCOPE, and the SEPR, we should also rely on the eco-design regulations. In this case, the 2016 regulation for high temperature processes. And in 2015, for low to medium, and low temperature processes. So here we already have double regulation, both the 14.825, which in the end will not define as much, just like with the SEER and the SCOP, those temperature profiles and partial loads. But we also have to talk about eco-design, as we mentioned in the previous video about SEER and SCOP. These units are already eco-designed, since in the end we need to know where they will be installed and how they will operate in order to ensure they are efficient. All right, here we would have the SEPR for high temperature and for medium temperature. We'll see that for low temperature, it's at -25 degrees Celsius supply temperature. This would be for the cooling only version. And here we would find the SEPR, as you can see, we would also maintain that 7 degrees supply and those -8, but it would be for a reversible air-to-water unit operating in cooling mode. All right, as before, we would need to define the climate zones where the unit will operate and the partial loads at which we must simulate its operation to perform the calculations. What are the climate zones? Well, in this case, we find that the 14825 standard for process chillers, which will operate in cooling mode, gives us this histogram for air to water. As a note, notice that it does indeed operate 100% of the hours in a year, those 8,760 hours, because a process chiller in industry can actually be running all those hours, or close to that amount. And the temperatures will range from -19 degrees up to 38 degrees. What would the histogram look like for a water-to-water unit? Well, it will also operate all the hours of the year, 100%, but notice how the temperature range decreases. The temperature range decreases because we are not working against air, but rather against well water, water from a cooling tower, or a district heating loop. The operation of air-to-water and water-to-water systems is somewhat different, but in the end, if you look at it, it's simply a histogram where we work based on either air or water temperatures and the number of hours it operates throughout the year. What are the partial load conditions that we need to consider? All right, so for this equipment, for air-to-water process chillers, we will use approximately 80% for 3 degrees of outdoor air temperature, 87% for 15 degrees, 93% for 25 degrees of full load, and 100% for 35 degrees outdoors, which is what Eurovent specifies. In other words, we don't change anything here. So, well, there are no surprises here either. For water-to-water operations, we will find the same thing, but of course, all of it refers to that water temperature in the external heat exchanger. Finally, if we look at the equipment's data sheet, we will see that we have that EPR with a supply temperature at 7 and at -8, operating in cooling mode and working as a process chiller, which is different from the SAR. It's completely different from the SAR. And we will define that it operates at high temperature when the water supply temperature is 7 degrees. At medium temperature, when the water supply temperature is -8, and at low temperature, when we are working with a water supply temperature of -25 degrees. So, in cooling mode, we would have the SPR for supply at 7, which is high temperature, or at -8, which is medium temperature. And when the equipment is reversible, we will find the same situation with the SPR for high or medium temperature and operating as a process chiller. That's all. As you have seen, the concept of SEPR and SCOP compared to SPR, apart from the fact that SPR is only for cooling mode, is somewhat different. It's different because of the number of hours it operates, and it's also different because it includes that concept that, as you may have noticed, it will operate between 80 and 100% most of the time. So these are systems that will be operating very close to or almost always near their nominal conditions. All right, see you in the next video where we will look at the ETAs, the seasonal efficiencies. Best regards,